The goal of this first lab is to help us visualize the interactions between point charges, whether it be between a negative and a positive point charge, between two positive point charges, or a positive and neutral point charge. This experiment is set up in a way so that we will be able to approximate how much excess charge is on one piece of charged tape. In order to do this, we will need to account for the gravitational force acting on the charged tape and the electrical interaction acting on the charged tape. The materials needed to complete this lab include a ruler, clear Scotch tape, and 2 books of equal height. The U-tape is formed by measuring out about 20 centimeters of tape. Next, fold over one end of the tape to create your handle. Then place this tape on a flat surface. Repeat this process, but place the next tape over your base tape. Then strip the top tape from the base tape and you now have your U-tape. The next part of the experiment asks us to predict and observe a series of events. First, we must observe the interaction between two U-tapes. As I expected, the two U-tapes repelled each other. This can be visualized in the image. A negative charge is created on a clear plastic pen by rubbing the pen through our hair. We are then asked to observe the interaction between the pen and one U-tape. As you can see in the image, the pen and the U-tape are attracted to each other. This also tells us that the U-tape must have a positive charge. One other observation was made between a positive U-tape and a neutral object. As I did not expect, there was a slight attraction between the two objects. This diagram is the experimental layout used to estimate the excess charge on one U-tape. Since the momentum of tape B is not changing, we can conclude that the net Y component of the force on tape B is 0. The main vertical forces on the floating portion of tape B include the negative gravitational force and the positive repulsive force from tape A. If you place tape B on the books so that there is sufficient slack, the tension forces from where the tape is attached will be negligible. Here is the free body diagram for tape B. There is a negative gravitational force and a positive repulsive force from tape A. As you can see, these two force arrows are of equal length but in opposite direction. In order to find the gravitational force on tape B, we must find the mass of tape B. I found the length of tape B to be about 0.195 meters. We are given that every 1 meter of clear tape has a mass of 1 gram. By multiplying the tape length by this factor, I found the mass of tape B to be 1.95 times 10 to the negative 4 kilograms. In order to find the gravitational force acting on tape B, I multiplied the tape's mass by the gravitational constant. In my coding, I called it grav, which is equal to negative 9.81 meters per second squared. I found the gravitational force on tape B to be equal to negative 0.001913 newtons. Here's my experimental setup for Lab 1. I made sure to attach tape B to the books such that there was sufficient slack. I measured the separation distance at which tape B began to float to be 0.022 meters. In order to solve for the charge on tape B, there are some key assumptions that one must make, which include 1. To treat the U-tape as a point charge, and 2. Assume the U-tapes have the same net charge. And that is a reasonable assumption because the U-tapes are of equal length and made by the same process. First, I created a radius vector for the distance between tapes A and tape B. I then converted this radius vector into a unit vector. I then plugged these components into the equation for a force produced by a point charge, in this case the repulsive force from point A. I solved the value of Q by manipulating the net Y component of the force equation using simple algebra. You can see my work in the top right corner. Ultimately, I found the charge on tape B to be equal to 1.014 times 10 to the negative 8 coulombs. To solve for the number of deficit electrons, I divided the total charge of tape B by the charge of an electron. I found the number of deficit electrons to be 6.34 times 10 to the 10. To find the number of atoms on tape B, I defined the surface area of an individual atom. I did this by dividing the length of an atom by 2, then squaring that and then multiplying that by pi. I then divided the total area of my tape by the area of an individual atom to find my number of atoms. I found my number of atoms to be 4.72 times 10 to the 17. The image to the left is the coding I used for this lab, and the image to the right is a model produced by this code. As you can see, this code prints out the charge of tape B, the number of electrons deficient, the number of atoms on tape B, and the ratio between the electrons deficient and the atoms on tape B. The green sphere represents tape B. The purple arrow protruding up from the green sphere represents the repulsive force from tape A acting on tape B. The red arrow protruding down from the green sphere represents the gravitational force acting on tape B. Overall, this lab helped us visualize the interactions between point charges. In order to solve for the excess charge on tape B, we needed to implement key concepts including summation of forces and Coulomb's law. the low ratio for electrons deficient to number of atoms on tape B in the case that not all atoms lost electrons. To improve my lab results, I should use a different mechanism for propping up tape B. The books often fell and interfered with my ability to interact tape A with tape B.